Hello and welcome to Engineers Mindset Academy. So in today's video, we are going to be talking about the Buckingham's pi method of dimension analysis. As we all know, there are two methods to carry out dimension analysis. The first method is the Rayleigh's method, and the second method is with the use of the Buckingham's pi method. Now, the Buckingham's pi method has an advantage over the Rayleigh's method in that the Rayleigh's method cannot exceed more than 5 independent variables, whereas the Buckingham's pi method can evaluate up to more than 5, 6, 7 independent variables. Now, what is the Buckingham pi method theorem all about? The theorem simply states that if there are n dependent and independent variables in a dimensionally homogeneous equation, and these variables combine together to form m fundamental quantities, then they are arranged in such a way to obtain n minus m dimensionless terms called pi terms. I will take that again. The theorem simply states that if I have n dependent and independent variables, if I have a total of n dependent and independent variables, and these variables combine together to form m fundamental quantities, quantities. These fundamental quantities are simply the m, the l, and the t systems of measurements, mass, length, and time systems of measurement. So if I have n dependent and independent variables in a given homogeneous equation which form m fundamental quantities, or which combine to form m fundamental quantities. Now these variables are arranged in such a way to obtain n minus m dimensionless variables. Okay, dimensionless terms or variables. Dimensionless terms or variables. These dimensionless terms are called pi terms. All right, these dimensionless terms are simply called pi terms. Once again, n stands for the total number of both dependent and independent variables in the equation. Secondly, m here stands for the fundamental quantities found in the dependent and independent variables as found in n. Then you combine them to form n minus m dimensionless terms. These dimensionless terms are called the pi terms. So let's take this particular question on the board for an example. All right, so the question simply says the resistance R experienced by a partially submerged body depends upon the velocity v, length of the body L, viscosity of the fluid mu, density of the fluid rho, and gravitational acceleration g. The question says obtain a dimensionless expression for R. So the first thing to do whenever you encounter questions in dimensional analysis, let's pick out what all the parameters or the terms given. That's the first thing to do. So we are given that the resistance R, so you have resistance. All right, so let's simply call this, so let's call this step 1. Step 1, you have that resistance R depends on, it depends on velocity v. The second thing there is length of the body, so length L. The third thing there is viscosity of fluid, viscosity mu. The fourth thing there, the fourth thing there is density. So you have density of the fluid, rho, and the final thing there, which is the 15, is gravitational acceleration, simply gravity g. All right, so we have that the resistance R depends on this whole quantity. This is the first step. The second step, step 2, the second step is to form what is called the functional equation, right? Or you form the functional equation. That's the second thing to do. Now, what's the functional equation? Resistance R depends, which means arrow is equal to a function of velocity v, the length L, the viscosity mu, the density rho, and gravity g. This is the second thing to do. Second step is to write the functional equation. Resistance is equal to is a function of all of this. From the question, resistance depends on. So if resistance depends on, it means that resistance itself is a dependent variable. So we have R to be the dependent variable, whereas every other term here are the independent variable. Okay, every other term here are the independent variable. So remember from the theorem, the Buckingham's pi theorem, it says if we have n number of dependent and independent variables, so R, which is the resistance, depends on the whole of this, which makes R a dependent variable, and therefore the whole of this are what? The independent variable. Now, step 1, like I said, you write out all the parameters given to you. Step 2, you write the functional equation. So this is simply called the functional equation. R is a function of the whole of this. Step 3, you rearrange the functional equation and include R into the brackets. So we have a mixture of both dependent and independent variable. That's the third step. So step 3, you're going to have, step 3 is simply going to now be f1. So simply call this function now f1 into, I will send arrow into the brackets. It becomes arrow, velocity, the length, the dynamic viscosity, density, and gravity. The whole of this is equal to 0. You can simply call this equation 1. So this is the third step. This is the third step. Simply send arrow into this bracket. Now, why do you send arrow into the bracket? You want to obtain the first theorem. The first thing said in the theorem of Buckingham's pi method. If there is n number of dependent and independent variables, so they must be together. So therefore, the total number of dependent and independent variables becomes now 1, 2, 3, 4, 5, 6 variables, where arrow is the dependent variable and these other 5 are what? The independent variables. Okay, so which means total number of dependent and independent variables are what? Equal to 6. So from the Buckingham's pi method, n dependent and independent variables, n is simply equal to 6. Okay, this is now the fourth step. Okay, so this is going to be the fourth step. All right, so let's put it out. Step 4, or the fourth. Okay, step 4. All right, so this is the fourth step. N is simply equal to what? 6. Total number of dependent and independent variables. So you simply count all of them together: 1, 2, 3, 4, 5, and 6. Hence, n is equal to 6. Now, if you observe in the theorem states that if we have total number of dependent and independent, or n dependent and independent variable in a homogeneous equation, and these variables combine to form the fundamental equation m. So which means we need to find their dimensions. So we need to write the dimensions of all the physical variables involved here. That will be the next step. So step 5 is to write the dimensions or dimension analysis of each of the given function involved. So I've made separate videos on Rayleigh's method of dimension analysis. I'm going to post that link in the description of the video so you can watch how to dimension physical variables. All right, so we're going to be writing the dimension of each and every term involved here. That's the fifth step. Okay, so let's start with the resistance. Resistance, mind you, is a force. Resistance is a force, and we know that force is always given as mass times acceleration due to gravity. And I've always said that the best way to write dimension of physical variables is always from their units. How is that possible? The dimension of mass already is constant, is still capital M. From dimension theorem or from dimension analysis theorem, we have the M, L, T systems of dimensioning, where M stands for mass, L stands for length, and T stands for time. So force is mass times gravity. Mass remains capital M by dimension. Gravity itself, we know the unit of gravity is meter per second squared. The unit of gravity is always meter per second squared, where meter stands for the unit of length. Meter stands for the unit of length. So we have length here. That means gravity is simply what? L all over second squared. Second stands for time. So, and time by dimension is what? Capital T. This is now L all over T all squared, because this is second squared. That means gravity is actually what? L T to the power of minus 2 by rearranging this. Okay, converting this to multiplication, this becomes L T to the power of minus 2. So, which means by dimension analysis, force can simply be what? Mass times what? G, and in place of G, this is G, this becomes MLT to the power of minus 2 by dimension. So force is equal to, or resistance there is a force, and it is simply equal to MLT to the power of minus 2. That is the first. Second, there is length. Dimension of length is, of course, length. It still remains length. So dimension of length is still equal to length. It remains L. The next there is the viscosity. Now, what is the unit of viscosity? I've always said the best way to dimension physical variables is always from their unit. What is the unit of viscosity? Viscosity, mu, is measured as Newton seconds per meter squared. This is the unit of viscosity. Newton seconds per meter squared. Once again, seconds is time. And again, meter there stands for what? Length, unit of length. Then we need to find Newton. Newton is the unit of force. And we have just found force to be equal to what? MLT to the power of minus 2. So all we need to do is to what? Put in these values into the unit of viscosity. Therefore, viscosity is equal to, in place of Newton, MLT to the power of minus 2 times seconds there. And seconds in unit of time, dimension of time, which is capital T. You have this all over m meter squared, and meter is what? L stands for the dimension of meter. So you have all over L all squared. So from here, L here cancels one of the L here. This is T to the power of minus 2 multiplying by T. So mu becomes equal to what? This is M. Remember, I have one L under here. So if I pull it up, it becomes L to the power of minus 1. Then this is T to the power of minus 2. Whereas this is T to the power of 1. By indices, when two terms having the same base multiply one another, pick one of the term and add their powers. So minus 2 plus 1 remains minus 1. So which means the dimension of viscosity is simply what? ML to the power of minus 1, T to the power of minus 1. So for viscosity, mu, we have ML to the power of minus 1, T to the power of minus 1. We have this. The next on the table is density. And we know that density is mass all over volume. Now, in this case, you don't need to use the unit. You can simply say density is mass all over volume. You can also go by the units. Okay, kilogram is unit of mass, but by dimension, mass still remains capital M. But by the volume, by dimension, volume is simply meter cube. The unit of volume is meter cube. And meter stands for what? Length. Okay, by dimension, meter stands for the length. Alright, so meter cube now simply becomes what? L to the power of 3. So which means density is actually mass L to the power of minus 3 if you rearrange this. So density, rho, is simply what? M L to the power of minus 3. And finally, we write the dimension of gravity. We've already done this earlier. Okay, we've already done this earlier. Gravity itself, G, the unit of gravity is meters per second squared, where meter is the unit of length. So you have L all over, seconds is unit of time, but this is second squared. By dimension, time is capital T all squared. So if you arrange this, you're going to find that gravity is L T to the power of minus 2, and you have this. So that is the fifth step. Okay, write the dimensions of each of the given physical variables or each of the given dependent and independent variable involved in the equation or the functional equation. All right, now having written down this, the theorem states that if the total number of dependent and independent variables combine to form m fundamental quantities, what does this mean? It means that do they form MLT system or do they form MLT amongst all of them? So you look through them, resistance alone forms MLT. L is still here, G forms LT, ML here, and MLT once again. So which means the combination of both dependent and independent variables forms MLT system amongst them. We have M, we have L, we have T. This simply means that step 6, M is equal to 3. The total number, because they all form what? MLT. They all form MLT. Total number of dependent and independent variables combined to form MLT. So this MLT gives us a total number of 3, which means the number of fundamental quantities involved there is 3. The number of fundamental quantities involved is simply what? 3. All right. Now, if you have this, the final thing in the theorem states that if they form the fundamental quantities MLT, then they are arranged in such a way that they form n minus m dimensional terms, which are called the pi terms. So step 7 is to form what? N minus m dimensional terms, which are called the pi terms. Now, what is m? This simply implies what is n? N is total number, which is what? 6. Total number of dependent and independent variable will give us 6. So you have 6 minus what is m? M is the number of fundamental quantities involved, which is 3. 6 minus 3 simply gives us what? 3. So this simply means we are going to have 3 pi terms. Hence, we have 3 pi terms. That is what it means. It means we are going to have 3 pi terms. Now, the 8th step is to rearrange the first equation, which is in step 3. Rearrange the first equation in terms of what? The pi terms. Okay, rearrange the first equation in terms of pi terms. So I'm going to have step 8 to now be equal to, okay, step 8 to now be equal to f1 into pi 1, pi 2, pi 3, because I have what? 3 pi terms. 6 minus 3, which is m minus m, gives us the number of pi terms. So 6 minus 3 is equal to 3. It means I have 3 pi terms. And that is simply what? f1 into pi 1, pi 2, and pi 3. And this is equal to 0, as can be seen in this equation 1 here. Everything there is equal to 0. So which means we are rearranging or writing equation 1 in terms of total number of pi terms. Okay, so you can simply call this maybe equation 2. Now, since I have pi 1, pi 2, and pi 3, it means I'm going to be forming 3 different equations of pi 1, pi 2, and pi 3, okay, to be able to find their values. Now, in these 3 different equations, these pi terms are called repeating variables. Now, what are repeating variables? Repeating variables are those variables that occur repeatedly in all the 3 equations. So, in equation 1, for the pi 1, pi 2, and pi 3, I'm going to have that same variable in pi 1. For equation 2, I will still have those same variables repeating in equation 2. For equation 3 for pi 3, I will still have those same variables repeating in that equation 3 for pi 3. So they are simply called repeating variables. Now, how do you select or choose a repeating variables? How do you select or choose a repeating variables? Quickly, there are 3 ways of selecting a repeating variables. First, a repeating variable must contain a geometric property. Secondly, a repeating variable must contain a flow property. Thirdly, a repeating variable must contain a fluid property. These 3 conditions are what you consider when choosing repeating variables. I will take it again. Firstly, repeating variables must contain a geometric property. Secondly, repeating variables must contain a flow property. And lastly, repeating variables must contain a fluid property. Now, what are geometric properties? Let's start from the first. First, we said it must contain a geometric properties. Geometric properties are those properties that talks about the dimension of a given variable, either the length, the height, the width, the area, and so on, the volume. These are all geometric properties. They are those properties that contain the physical dimensions of a given variable or a given quantity. All right. Then the second, we said it must contain a flow property. What are flow properties? Flow properties are those properties that propagate the flow of a fluid, that causes a fluid to what? Be in motion. Those properties that propagate the motion of a fluid is simply called flow property. Example include velocity, acceleration. These are all flow properties. What causes a fluid to flow are called flow property. All right. And finally, we said fluid property is the last one. Fluid properties. What are fluid properties? Fluid properties are those properties that characterizes the nature of a fluid. They are those properties which characterizes the nature of a fluid. Example include density, dynamic viscosity, kinematic viscosity. All of these are called fluid properties. Now, when dealing with the geometric property, if I have length and other geometric property in a given equation, always prefer length. If I have length, if I have head, if I have height, if I have diameter, if I have all of that area in a given equation, just like we have in this equation now, if I have all of that in a given equation, always prefer length than others as your what? Geometric property. Secondly, that of the flow property, if I have velocity, if I have acceleration in a given equation, always prefer velocity ahead of acceleration. Okay. And lastly, which is the fluid property now, if I have viscosity, if I have density, if I have maybe dynamic viscosity and kinematic, whatever, always prefer density above every other fluid property. Always prefer density. Except you can't find density, then you can switch to dynamic viscosity. All right. So let's fall back to the question now. We are on step 8 and we have been able to form the number of what? Pi terms involved. So this is where the main calculation starts from. So we need to select, like I said, we need to select repeating variables. These repeating variables will be found in pi 1, will also be found in pi 2, and will be found in pi 3. So step 9 is to select your repeating variable. So I'm going to wipe the question now, not forgetting the question says we should obtain dimensionless expression for R, which is the resistance. So what we are trying to do now is to find an expression for the resistance R. All right. So step 9 is to select repeating variables. And I said you select your repeating variables in such a way that it must contain a geometric property, it must contain a flow property, and it must contain a fluid property. And mind you, the 3 repeating variables selected must all combine to form the MLT fundamental quantities. So these 3 properties which you're selecting, these 3 repeating variables must contain MLT in them. They must all combine to form MLT in them. So let's look to the equation now. This is the equation. And also, another thing to note is, do not select the dependent variable as a repeating variable. Do not. So it is only the other 5, the independent variables, that we are going to select our repeating variables from. Okay, so keep that in mind as well. So it is clear we are not going to consider arrow because arrow is a dependent variable. So let's consider the other 5 options. I said in terms of geometric property, always prefer the length. So length is here. We have length to be the first repeating variable. Then I said in terms of flow property, always prefer velocity ahead of every other flow properties. So we have velocity here and we have gravity. These 2 are flow properties, but always prefer velocity ahead of gravity. So we choose V. And finally, the third property must contain a flow property. And I said amongst the flow properties, always select preferred density amongst every other. I have dynamic viscosity here, is a flow property. I have density, it is also a flow property, but always prefer density ahead of dynamic viscosity. So we simply pick density. So these are our three repeating variables. Now let's check and see if these variables contain or form the MLT systems amongst themselves. The dimension for length LC remains what? L. Dimension for velocity, unit of velocity, remember, is meters per seconds. I always say the best way to write dimension of physical variables are from their units. So meter per seconds, which means meter, remember, is unit of length. So by dimension, meter stands for L, all over seconds stands for time, which is T, capital T. So which means velocity is what? Rearranging this now becomes L T to the power of minus 1. This stands for the velocity. And density itself is mass all over volume. We already obtained dimension of density over here as m L to the power of minus 3. So density itself is simply m L to the power of minus 3. Now let's check and see if we are going to find the MLT fundamental quantities among the three of them. There is L here, there is T here, and there is what? M here. So which means the three of them jointly form the MLT system. So they are accurate. There is L, there is also L here, there is T, and there is M. So three of them form the MLT fundamental quantities. And again, the final rule, we have not selected the resistance as a repeating variable. So this is step 9. All right. Now, having found this step, I can simply wipe off these equations now, everything here, because I'm no longer interested in anything here. This is our fundamental equation. We are now solving for pi 1, pi 2, and pi 3. All right. Okay. So please just mind this equation 1. Mind this equation 1. We need to start solving for the pi terms. So let's start with consider pi 1, considering pi 1, the first pi term. This is what you do simply. Pi 1 is equal to the repeating variables. And repeating variables are what? We have the length to the power of a1, always take a1, times the velocity to the power of b1 times the density to the power of c1. Now, after forming this, it doesn't end there. Notice that in the fundamental equation, we choose, let me asterisk them, we choose velocity, we choose length, and we choose density to be our repeating variables. So which means we are left with what? 1, 2, and 3 terms. We choose velocity, we choose length, and we choose density to be our repeating variables. So which means we are left with the resistance, we are left with dynamic viscosity, and we are left with what? The gravity. Now, what you do is, the first term, pi 1, these are the repeating variables, they occur in all the equations, pi 1, pi 2, and pi 3. Now, after inserting the repeating variables, you multiply this by attaching one of the terms which you have not selected from the fundamental equation. So, I have not selected R1, I have not selected mu, I have not selected gravity. So, you can pick one amongst the three. But let's start from R. You simply append R over here. It's as simple as this. Then pi 2 is formed. Okay, pi 2 is formed. Same thing. These are called repeating variables. You pick them out again. This becomes L to the power of, now is A2 times V to the power of, now is going to be B2 times rho to the power of, this is now going to be C2 times, now I have chosen arrow. The next term left untouched there is what? Mu. You simply attached mu. Finally, for pi 3 is equal to same thing, L to the power of A3 times V to the power of B3 times rho to the power of C3 times the final term which you've not selected, and that is what? G, multiplied by G. So you can call this equation maybe x1, call this equation x2, call this equation x3. These are the equation for the pi terms. So this is all what we are solving for. Now you can discard this part of the equation. So mind you, whenever you select your repeating variables, they must always occur. That's why they are called repeated variables. You can see them in equation 1, you can see them in equation 2, x2, and you can also see them in equation x3. The only difference now is that the terms which have not been selected from the fundamental equation and now picked one after the other and placed in each of these equations. So it doesn't really matter. R can occur in equation x3 and G can occur in equation x2. It doesn't really, however you want to arrange it, it doesn't really matter. At the end of the day, you obtain the same result. All right. So we can discard now the fundamental quantity or the fundamental equation. So these are the three equations which we are solving for. You start with the first equation. For pi1, okay, for pi1, you have pi1 to be equal to LA1 times VB1 times rho C1 times R. This is our equation x1. You apply the principle of dimensional homogeneity to solve this problem. You apply the principle of dimensional homogeneity to solve this problem. What is the principle of dimensional homogeneity? It simply states that for a physical quantity or for an equation to be dimensionally homogeneous, the power of the variables on the left-hand side must be equal to the power of the variables on the right-hand side. Now, you agree with me that pi is a constant and every constant is dimensionless, which means you cannot dimension them. And it is usually termed as 1. The dimension of every constant is always taken as 1. So pi here simply can stand as 1. But how else can you write 1? Okay, 1 can also be written as dimension of pi can now be m to the power of 0 times L to the power of 0 times T to the power of 0. This remains dimension of pi, such that m to the power of 0 is 1 times L to the power of 0 is 1 times T to the power of 0 is also 1. 1 times 1 times 1 simply gives you what? 1. You simply have this to be 1. So which means to write pi as 1, it simply means to write it as what? M to the power of 0, L to the power of 0, and T to the power of 0. You are now employing the principle of dimensional homogeneity, which means you must have MLT system, however you want to do it, on both left-hand side and on both the right-hand side. Okay, so having this now to be the dimension of pi, then it means we can now rewrite this equation, okay, by putting in the dimension of the variables. In place of pi1, remember, it is m to the power of 0 times L to the power of 0 times T to the power of 0 for pi, and this is equal to dimension of length L still remains L. So you have L to the power of A1 times dimension of velocity. We just did that here, remains what? Lt to the power of minus 1. So in place of velocity, we have Lt to the power of minus 1. Remember, all to the power of B1. So to the power of B1 times rho, which is density. Dimension of density, we obtain that here as ml to the power of minus 3. So you have ml to the power of minus 3. Remember, all to the power of C1. So to the power of C1, okay, times arrow. Arrow there is the resistance, and we obtain dimension of resistance as what? mlt to the power of minus 2. So we have mlt to the power of minus 2. Be careful not to append arrow, mu, or g to any what? Unknown term. Just like we have A1, B1, C1. Don't append anything to any of these terms. All right. So all we need to do now is expand the powers, expand the bracket with the powers. So you have this to be m to the power of 0, L to the power of 0, T to the power of 0, and this is equal to L to the power of A1 times, if I expand this power with B1, it becomes L to the power of B1 times T to the power, remember this is T to the power of minus 1. Minus 1 times B1 becomes minus B1, okay? Times same thing here, m to the power of C1, so I have m to the power of C1 times L to the power of, this is minus 3. So minus 3 times C1 gives us minus 3C1, okay? Times m. Now, mind you, this m simply means m to the power of 1. L, same thing here. This L simply means L to the power of 1 and T to the power of minus 2. I have this equation like this. Okay, we can continue from here. M to the power of 0, L to the power of 0, T to the power of 0 is now equal to, now we rearrange the right hand side of the equation to be in terms of MLT, just like the left hand side is in terms of ML and T. Let the right hand side also be in terms of MLT. So bring all the terms with M together and all the terms with L together. So I have M to the power of C1 here, and I have M to the power of 1. Bring them together. This is M to the power of C1 times M to the power of 1 times. Now you move to the L terms. These are the only M terms we have. We move now to the L terms. I have L to the power of A1, L to the power of B1. I have L to the power of minus 3C1. Okay, L to the power of A1 times L to the power of B1 times L to the power of minus 3C1. It doesn't end there. I still have L to the power of 1 over here times L to the power of 1. Okay, finally for T, okay, we have T to the power of minus B1 here, and we have T to the power of minus 2 here. So for T, we have times T to the power of minus B1 times T to the power of minus 2. We simply have this. Okay, so M to the power of 0, L to the power of 0, T to the power of 0 is now equal to, what you do at this point is now employ your indices. The rule of indices states that when two terms having the same base are multiplying one another, you simply pick one of the terms and add their powers. So I have M multiplying M. They have the same base, M and M. Simply pick one of the M and you add the powers. Powers remains C1 plus 1. This is C1 and this is 1. Next is for L. I have L here. Add up the powers. A1 plus B1 minus 3C1. Remember, plus 1 over here. Times, finally for T, I have T here minus B1 and minus 2. It actually becomes minus B1 minus 2 for T. Alright, so the equation becomes this. Now, from the principle of dimensional homogeneity, like I said, the powers of each of the terms on the left-hand side must be equal to the power of each of the terms on the right-hand side for the equation to be dimensionally homogeneous. So that simply means that for M, then the power here, which is 0, must be equal to the power of M on this side of the equation, and power of M here is what? C1 plus 1. Call this equation, okay, maybe 1, whatever. Then for L, the power of L here is 0, so 0 is equal to the power of L on this other side. I have here A1 plus B1 minus 3C1 plus 1. Call this equation 2. Finally, for T, okay, I have the power of T here to be 0, and this is equal to the power of T on this side of the equation. You have minus B1 minus 2, minus B1 minus 2. Call this equation 3. So you observe that from equation 1, I can make C1 subject by sending plus 1 over to this side of the equation. This simply implies that C1 is equal to what? 0 minus 1. Of course, if plus 1 cross and equal to sign, it becomes negative. So I have 0 minus 1, and 0 minus 1 remains minus 1. This implies C1 is equal to minus 1. Same thing from equation 2. If I send minus B over to this side, okay, I'm going to have minus B crossing and equal to sign becomes positive. This becomes 0 plus B to be equal to, I'm left with what? Minus 2 here. This is minus B1, okay? So this is plus B1, okay? So I am left with what? Minus 2. So this simply implies that B1, of course, 0 plus B1 remains B1, and B1 is what? Minus 2. Now, if I have B1 and I have C1, I can put them into equation 2 to find the value of A1. All right. So we can now put in the values of B1 and C1 into equation 3. Into equation 2. In equation 2, I have 0 is equal to A1 plus B1. So I have A1 plus B1 is equal to minus 2. So it becomes minus 2. Then I have minus 3C1 minus 3. What is C1? C1 remains minus 1. So minus 3 times minus 1, okay, plus 1 plus 1. All right, so I have this. Now, this simply implies that 0 is equal to, I have A1, okay, minus 2, minus 3 times minus 1 becomes, minus times minus becomes plus, 3 times 1 is 3, so this is plus 3 plus 1. And of course, I have this to be 0 to be equal to a1 minus 2 plus 3 is 1 plus 1 is 2. So this is plus 2. And this simply implies to make a1 subject, send plus 2 over to this side of the equation. It means now that a1 is equal to 0 minus 2, which simply implies that a1 is equal to minus 2. So we have all the constants now. We have a1, okay, a1 to be equal to minus 2, b1 to be equal to minus 2, and c1 to be equal to minus 1. Having done this, we can now fall back into the original equation for pi1 and put in the values of a1, b1, and c1 into the original equation for pi1. If you do that, you're going to have, so I'm taking this off now. All right, so for pi1, we had L to the power of A1, and what is A1? A1 is minus 2, so this becomes L to the power of minus 2 times V to the power of B1. Again, B1 is minus 2, so this is V to the power of minus 2 times rho to the power of C, C1, and C1 is minus 1, so you have rho to the power of minus 1 times R. And of course, by rearranging this, we are going to have that pi1 is equal to r all over, this is L to the power of 2, this is V to the power of 2, and this is rho to the power of 1. So this is our pi1. It's as simple as this. Repeat the same procedures for pi2 and pi3. It's as simple as this. So this is our pi1. Okay, so I'm going to be keeping pi1 on one side of the equation. Since we'll solve for pi1, let me take this off for pi1 and write its value somewhere around here. So pi1 is equal to r all over L2, V2, and rho. Okay, so this is our pi1. All right, so we can take this off now. Then we start with pi2, doing the same thing that we've done, applying the principle of dimensional homogeneity to solve for pi2. Now, what is pi2? Pi2 is equal to, we have L to the power of A2 times V to the power of B2 times rho to the power of C2 now times mu, which is dynamic viscosity. This is equation X2. Now, if you have this, let's put in the values. By dimension analysis, you've already known that pi remains what now? Pi remains m to the power of 0, L to the power of 0, and T to the power of 0. And this is equal to, by dimension analysis, L still remains L. So this is L to the power of A2 times V. We know this already. Already we know that V is equal to LT to the power of minus 1. We've done this already. So in place of V, we have LT to the power of minus 1 all to the power of what? B2 times rho. We know what rho stands for, density, ml to the power of minus 3. So in place of rho, we have ml to the power of minus 3 all to the power of what? C2. So we have C2 times mu. Mu is the viscosity, and of course, we found viscosity to be what? ml to the power of minus 1, T to the power of minus 1. So in place of mu, we have m L to the power of minus 1, T to the power of minus 1. Okay, it's just like in the previous, we expand the bracket with what? These unknown exponentials. So this becomes m to the power of 0, L to the power of 0, T to the power of 0, and this is equal to L to the power of A2 times, if I expand the bracket with B2, this becomes L to the power of B2, okay, times T to the power, remember this is T to the power of minus 1, minus 1 times B2 gives us minus B2, okay, times, this is M to the power of C2, I have C2, L, remember L is to the power of minus 3 times C2 gives us minus 3c2 times m. Remember, this m here simply means m to the power of 1, L to the power of minus 1, T to the power of minus 1. We simply have this. So the next thing now is to rearrange the equation in terms of MLT. So we can apply the principle of dimensional homogeneity. So we have to rearrange the equation to be in terms of MLT, just as in the left-hand side of the equation. So for the left-hand side, we still have m to the power of 0, L to the power of 0, T to the power of 0, and this is equal to, now we rearrange the right-hand side to be in terms of MLT. So starting with m, I have m to the power of C2 here, and I have m to the power of 1 over here. So bring them together, m to the power of C2 times m to the power of 1. Next is L. You start with L next. L here is 8 to the power of A2. I have L to the power of B2, and I have L to the power of minus 3C2. This is L to the power of A2 times L to the power of B2 times L to the power of minus 3C2 times L, not forgetting, to the power of minus 1 over here. So L to the power of minus 1. Finally, we move to T. I have T to the power of minus B2 here, and I have T to the power of minus 1. So T to the power of minus B2 times T to the power of minus 1. Okay, so m to the power of 0, L to the power of 0, T to the power of 0 is now equal to, so from the principle of indices, remember, pick one of the terms and add up their powers. I have m to the power of C2 multiply m to the power of 1. Since they have the same base, m and m, simply pick one, add up the powers. It becomes C2 plus 1. For L, see the same thing for L, add up all the powers, A2 plus B2 minus 3C2 minus 1, and for T, add up the powers, minus B2 minus 1. I have this. Now, from the principle of dimensional homogeneity, the powers on the left-hand side of the equation must be equal to the powers on the right-hand side of the equation. So for m, remember, the power of m here is 0, and it must be equal to the power of m on this other side of the equation. I have C2 plus 1. Call this equation 1. So let's simply find C2 at once. From here, C2 is equal to, simply send my plus 1 over to this side of the equation. It becomes 0 minus 1, which remains minus 1. So C2 is simply minus 1. For L, remember, the power of L here is 0. It must now be equal to the power of L on this side of the equation. So I have A2 plus B2 minus 3C2 minus 1. Call this equation 2. Finally, for T, the power of T on the left-hand side is 0. It must also be equal to the power of T on the right-hand side, which is minus B2 minus 1. I have minus B2 minus 1. Call this equation 3. Let's simply make B2 subject. Send minus B2 over to this side of the equation. Negative sign cross an equal to sign becomes positive. So I have 0 plus B2, which remains B2. And this is equal to what? Minus 1. So B2 is equal to minus 1. Now, having known B2 and C2, we can plug that into equation 2 to find the value of A2. Okay, so from equation 2 we have 0 is equal to, remember, A2 plus B2 minus 3C2. A2 is unknown. A2 plus B2, what is B2? B2 is minus 1, so it becomes minus 1 plus 3C2, right? Okay, minus 3C2 minus 3, C2 is minus 1, so times minus 1, not forgetting minus 1 over here, so minus 1. This is now equal to A2 minus 1, minus 3 times minus 1 is plus 3. Okay, put down your minus 1 over here. Okay, so 0 is equal to A2 minus 1 plus 3 minus 1 should give us 1 plus 1. Okay, that should give us plus 1. So to make A2 subject, simply send plus 1 over here. This implies now that A2 is equal to when positive sign cross an equal to sign, it becomes negative. I have A2 to be minus 1. So we found A2, we found B2, and we found C2. We can now plug it back into the original equation for what? Pi 2, just like we did in the first case. So I'm going to wipe this side off now to obtain the value of pi 2. Alright, so pi 2 is now equal to, remember, L to the power of A2, and A2 is equal to minus 1. So this is L to the power of minus 1 times V to the power of B2. Once again, B2 remains minus 1. So you have V to the power of minus 1 times rho to the power of C2, and C2 also remains minus 1. So rho to the power of minus 1 times mu. And if you rearrange this is going to be mu all over, since this is to the power of minus 1, it means they are going to be coming down. So it becomes all over L, V, and rho. So this stands for our pi 2. So we can now take this off for pi 2 and write the original value of pi 2. So the final thing to do is to solve for what? Pi 3. Okay, so pi 2 is equal to, remember, mu all over L times V times rho. Okay, so this is our pi 2. All right. Finally, we solve for what? Pi 3, which is the final Buckingham's pi function. So we solve for pi 3. So it's just the usual thing, nothing really big. Solving for pi 3, remember pi has a constant, and from dimensional homogeneity, pi stands for what? M to the power of 0, L to the power of 0, C to the power of 0, and this is equal to, from dimensional analysis, LC remains L. So you have L to the power of A3, V remains, okay, LC to the power of minus 1. In place of V, we have LC to the power of minus 1. Remember, all to the power of B3. So all to the power of B3 times rho. Rho simply stands for what? Density, which is ml to the power of minus 3. So times ml to the power of minus 3, all to the power of C3. Okay, now multiply by G, gravity, and gravity is LT to the power of minus 2. So multiply by L, T to the power of minus 2. Okay, so as usual, expand the bracket now with the powers. I'm going to have m to the power of 0, L to the power of 0, T to the power of 0 to now be equal to, this remains L to the power of what? A3 times, this is L multiplied by, the power here is 1, multiplied by B3. This gives me L to the power of B3. Same thing, T, the power of T here is minus 1. Minus 1 times B3 gives us minus B3. I have here m to the power of 1 multiply C3. Okay, that gives us m C3. L minus 3 multiply C3 gives us minus 3 C3. Remember, L here is same thing as L to the power of 1, and C here remains T to the power of minus 2. Okay, so m to the power of 0, T to the L to the power of 0, T to the power of 0 is now equal to, now we rearrange these terms on the left hand side, on the right hand side, sorry, to be in terms of MLT, just as the left hand side. So we start from m. I have m to the power of C3 here only for m. Okay, so you pick it out, m to the power of C3. After m, the next is L. I have L here to the power of A3 times, I have L here to the power of B3 times, I have L here to the power of minus C3. So L to the power of minus 3, C3, sorry. Okay, I think that's all for, okay. And I still have L to the power of 1 here. So times L to the power of 1 over here. Finally, we move on to T. I have T to the power of minus B3 here. T to the power of minus B3. And I have times T to the power of minus 2 over here. I think that's all. All right. The next thing to do is, of course, employ the principle of what? Indices, to arrange them in terms of MLT. Okay, so we can do that over here. So we have m to the power of 0, l to the power of 0, t to the power of 0 to now be equal to, from indices, two terms having the same base, multiply one another, pick one of the base and add the powers. Fortunately, m here is just m on its own to the power of c3, right? Yep. Then next we move to L. I have L to the power of A3 here, L to the power of B3, L to the power of minus 3C3, and L to the power of 1. So we'll move to L, L to the power of A3, add up the powers, plus B3 minus 3C3 minus 1. That is for L. Okay. Oh, sorry, plus 1. That is plus 1. All right, thank you. Finally, for T will have minus B3 and minus 2. So for T, add up the powers, minus B3 minus 2. All right. So from the principle of dimensional homogeneity, the power of the variables on the left-hand side of the equation must be equal to the power of each variables on the right-hand side of the equation. So for M, we have 0 to be equal to the power of M on this side, which is C3. So this simply implies that C3 is equal to 0. For L, the power here is 0, and that's equal to the power of L here remains A3 plus B3 minus 3C3 plus 1. Okay, call this equation maybe 2 because this was supposed to be 1. And for T, finally, the power of T here is 0, and this is equal to the power of T on this side remains minus B3 minus 2. So we have minus B3 minus 2. Call this equation 3. So to make B3 subject, simply send minus B3 over to this side of the equation. Negative sign cross an equal to sign becomes positive. So I have 0 plus B3, which still remains B3, and this is equal to minus 2. So we have minus 2 down for B3. Now we know B3, we know C3. We can simply plug that into equation 2 to find the value of A3. So from 2, I have 0 to be equal to A3 plus B3, and B3 is minus 2. So minus 2 minus 3C3. C3 itself is 0, so times 0 plus 1. And this is going to be what? A3 minus 2. Of course, minus 3 times 0 is 0, so I'm left with plus 1. Okay? And this simply implies that 0 is equal to A3 minus 2 plus 1 is minus 1. And therefore, to find A3, you simply send minus 1 over to this side of the equation. Negative sign cross an equal to sign becomes positive. 0 plus 1 remains 1. So A3 is equal to 1. All right. So having this now, we can now write the fundamental equation for pi 3. We can now write the equation for pi 3. I think we are very much in order. So writing the equation for pi 3 is now equal to, we said, L to the power of A3, and A3 gave us 1. So this becomes L to the power of 1 times B to the power of B3. B3 gave us minus 2. So you have minus 2 times rho to the power of C3, and C3 is 0. So this is rho to the power of 0 times G. We have this. And of course, any term to the power of 0 remains 1. Rho to the power of 0 is simply 1. So this is going to now be written as what? G times L1, or G times L. L to the power of 1 remains L. So I have LG all over. This is V to the power of minus 2. So it comes down all over V to the power of 2. So our pi 3 is simply what? LG all over V to the power of 2. We have this for pi 3. So we'll find pi 1, pi 2, and pi 3. We can now plug them back into the fundamental equation of the pi theorem. Okay? Into the fundamental pi theorem equation, which is, in this case, is equation 2. So we have F1 into pi 1, pi 2, pi 3, and we said this is equal to 0. So F1 into pi 1. What is our pi 1? Pi 1 here is R all over L squared V squared rho. So we have R all over L squared V squared rho, okay, comma, pi 2. And what is pi 2? Pi 2 here is mu all over L V rho. We have mu all over L V rho. And finally, pi 3. Pi 3 gave us here to be Lg all over V squared. The whole of this is equal to 0. Now be very careful at this point. We are solving for a term of r from the question. Remember, write a dimensionless expression for r. So remember that r was the dependent variable. So you pull out r from this bracket. You're going to have something like this: r all over L squared V squared rho, and this is going to be equal to, mind you, immediately you pull out this arrow over to this side of the equation, you introduce this function, okay, into, now the bracket will take a different order. Please take note. If you are pulling out this arrow out of the equation, then everything here will rearrange. The denominators here will go up, numerators will come down. Same thing. So I'm simply going to have LV times rho all over mu. Immediately you pull out arrow from this bracket, then this rearrangement will change. The orders will change. Denominators will move up and numerators will come down. Same thing here. This becomes V squared all over L times G. You have something like this. Now you have to write an expression for r. Therefore, r is equal to, simply cross multiply the whole of this, multiply everything here. I have L squared V squared times rho function into L V rho all over mu into V squared all over L times G. This is the expression for the resistance R from Buckingham's pi method. What a long video and what a long calculation. All right, guys. Of course, the video is long. In the next video, we can do another question on Buckingham's pi method of dimension analysis. Thanks and cheers.